45 minutes later, I had 2 mile. And then I turned around and run the 4x4. I'm like, Coach, I'm done. Stop. I quit.
Oh.
I've not gone to that 4 or 5 times. So it was bad. It was bad experiences. I mean, they were fun, but
yeah.
it would have been fine until the 4x4. The 4x4 is a kid. Every time I'm like, Coach, I'm not a sprinter. You gotta realize me splitting a 57 is not gonna help you.
Yeah. My senior year, state was rough because I had 4 events and we do prelims and finals. So I did 400, 300 hurdles, 100, 100 hurdles, 2 days in a row. And like the first day I PR'd in like everything, and the second day was snowy. It was not fantastic.
Yeah. Kind of insane. I had the 800 the first day. I wasn't even supposed to have done the 800. I'm like, whatever, it's my senior year, I'll go see if I can place on all 3 of them.
There you go.
And we went out on a freaking 54, 55. I'm like, all right, this is dumb. Anyway, that race just. And then I seriously, about halfway through that race, I don't even remember what was going on. There was a point in that race I thought I was gonna pass out. It was hot. I was so tired. It was even 800. That race was fire and passion was hard.
That's what I told John. I'm like, I will complain about whatever you want to put me in besides the 800. Put me the 800, I will complain. I will. I will complain.
I remember on my even running 800. 80 days. This is nothing fun about it.
They just sound, I've never known, but they sound so bad.
Just take the 400 and double it.
Yeah, exactly. Do it twice. And the 400 is bad enough when you learn that it is a sprint the whole time. Then I can't imagine doing that again. Ugh.
That is 800.
Right. Well, let's go ahead and begin. Good to see all of you. Thanks for making it out today. I know you have exams and lots of other things to do in other classes, so appreciate you coming. I just want to go over some housekeeping items to start off with. This is our schedule. It's evolved a little bit from the beginning of the semester, but should be relatively final at this point. So today we will cover chapter 11, and I have an assignment for you on that. That'll be due on Tuesday at our next class. We'll talk about that in a moment. For next Tuesday, we'll talk about physical activity epidemiology, and have lots of great practical examples for you there. And then April 7th, so a week from today, we'll have another review activity in class to help get you ready for the 3rd exam. So that will involve spreadsheet as well as concepts. And then the following Tuesday, April 12th, that'll be in class, exam 3. And that's the week of our mini spring break. So we don't have class on Thursday, April 14th. April 19th and 21st, I want those to be work days. So I want you to work on finishing, getting your data collection completely done, getting your PowerPoint presentation ready, because the following week, April 26th and 28th, that's when you'll be giving your research presentation in class. So presenting all of your results and sharing with the class, being prepared to answer questions and so on. So at this point, how many of you have your data collection scheduled and or started? Okay, getting there. Don't come to me on Friday, April 22nd and say, do you have any time tonight to help me? Because I won't. Okay, so April 21st is the day. It has to be done by then. So, and then we have our final on Tuesday, May 3rd. And that will be non-comprehensive, just over chapters 11 and 17. So let's talk about your assignment. And so that's what you have in your hand here. It is on D2L, so you'll notice that there's a link to follow, and this is on the NFL Combine, because the NFL Combine is a good topic when we talk about validity and reliability. So please don't feel like you need to type in that link. You could just go to D2L, click on it, and then you'll have the questions there to fill out for that. The other questions, you'll have an article by Schoenfeld that is on D2L, so you'll answer those questions. All of the other questions are pretty well covered in the PowerPoint, so you want to go back through the PowerPoint and look at those concepts, and those answers can be found there. So this will be due on Tuesday. Is there any questions on that part? Okay, so for today, there are 3 parts. So if you go to the March 31st folder, you have the Chapter 11 PowerPoint, the Schoenfeld article from 2020 that's part of your assignment. You have the Chapter 11 assignment that you can get that link to. And then we have 2 different spreadsheets to review. One we will start with is the ANOVA practice. So I want you to make sure you're prepared, and this will be just another tool that you can use for the exam to help you with the exam. So we'll do that to start with, and then step 2 will be go through Chapter 11, and then step 3 will be the interclass correlation practice spreadsheet. And so we'll do those things in this order. So if you'd like to have the PowerPoint and then a couple of those spreadsheets, I would like to start with the ANOVA practice. If you could get that pulled up, we'll take a look at that. Okay, so that looks like this. And so this particular study involved 5 participants, and each participant did the bench press under 3 different conditions. So remember, with ANOVA, it's more than 2. So if it's 2, what test do we use? Yeah, so it can be an independent or dependent t-test. With ANOVA, that's when you have more than 2. So so it could be 3, 4, 5, and so on. So 3 is a nice number, so we'll use that. So 3 different conditions, 5 participants did a bench press under different conditions. So the bench press in condition 1 was performed with prior antagonist row set to failure. So from a muscular standpoint, what is an antagonist? What do we mean by that? Yeah, so essentially in this case, what they did is a set of rows, because a lot of those muscles are antagonists to the muscles that you use to bench press with. And so they did a set of antagonist rows to failure, and then they did their bench press. And then this was their peak power output for a bench press. So these numbers that you see here are in watts. So as those of you who've had biomechanics know, it's watts that we assess power. So condition 2 was the bench press with prior agonist PNF stretching. So what was done in this case? Agonist means what? Yeah, so the muscles that were involved in bench pressing. So a PNF stretch for the pectoralis major, a PNF stretch for the triceps, just before doing the same bench press procedure and then taking the peak power here. So that's condition 2. Condition 3 was a bench press throw. So how many know what that is? It's just like it implies. It's a normal bench press. You're stopping at the end of the range, and this one you're throwing it. So, and then you can see the power output here. So 5 participants did each of 3 conditions. So what we want to find is, first of all, is there a significant difference somewhere? And so that's where we use our F table. So if you have that with you, if you have your F table with you, that was that handout from the other day, you'll want to get that out. And then if the F ratio exceeds the critical value from the table, then we know that there's a significant difference somewhere between the conditions. So if there's a significant difference somewhere between condition 1 versus 2, 1 versus 3, 2 versus 3, and so on, how do we determine or pinpoint where that's at? What do we have to do? What's our second step after the F ratio? Post hocks. So those are follow-up comparisons that we use. There's lots of different post hocks that if you go on to graduate school, you'll probably have SPSS, and you can do LSD and Bonferroni, and Chef is the one that this particular author likes, is the Chef method, so we'll use that. But that's where you pinpoint where the particular comparison is significant. So first of all, we have how many conditions? There are 3. How many total observations? So 5 observations times 3 conditions is, we have 15 total observations. So looking at your F table, actually, can I borrow that for just a moment? So for the F ratio, it's in the numerator, what's the degrees of freedom? It's going to be number of conditions minus 1. So there are 3 conditions here. Minus 1 is 2. So you're going to be looking at 2 across the top. 2 across the top. And then it's total observations minus the number of conditions for the degrees of freedom in the denominator. So total observations is 15. Okay, 15 total observations minus 3 conditions is, it's going to be 12. So you're going to look down here, and where those numbers come together, 2 and 12. What are you seeing there? Yes, 3.885 is the critical value. So when we run this single factor ANOVA, that's what the F ratio needs to exceed for significance. So let's go ahead then, and we can go to our data analysis tool here. And so you're all set up, so data analysis. And we want the very first choice. Very first choice is the ANOVA single factor. So single factor ANOVA, which means that there's just one factor, it's bench press, but there's 3 different conditions under bench press. So the bench press is our single factor, but a factor can have multiple conditions underneath it. So we just click there, and then we click OK. All right, so on your input range, it's very important that if you're doing an ANOVA, that you have it set up just the right way. Excel is really nice, but as long as you have everything set up just perfect, and especially you want to make sure you're including your labels, because that'll make it easier to identify which means are associated with which condition. So you'll click here, And then you'll want to highlight everything across, just the conditions and the numbers, all the way down like that. Just take your time, making sure that you've got the condition and then all 5 numbers underneath it. So that's your power output. Then you can hit enter. And then you'll want to click on labels. So it'll include labels in that first row. And then on your output range, I've set this up to where you can put your output right here on this cell highlighted in yellow. So on cell A11, let's put our output right there. So hit enter. And so is everybody good at this point? Okay. So then we click OK, and we have all of our output here. So you can see ANOVA single factor, and you have your 3 conditions. And if we scroll across, you've got your averages right here. That's really important because you'll want to use that for your post hoc comparisons, your averages. So if you want, you can take that and just, because you'll need this for your exam, so you can take it and just highlight it so you know that that's important. Okay, so next thing is our F critical value. Do you remember the value we got from the old-fashioned way looking at our table? Yeah, so that's very same as what the Excel tells us right here, is the F critical value is 3.885 and so on. So we know that at somewhere there's a significant difference, because how do you know that? If you were looking at this, what would you say? It'd be, yes, that's one way, because it is less than what? 0.05, yes. What's another way? Excellent. So this F value right here. And remember, the F value is determined by the mean squares between divided by the mean squares within. So sometimes the mean squares within is called the error variance. So if you have very little error or variance within groups or within conditions, and a large difference between conditions, that's going to give you a very large F value. So lots of difference between, very little difference within the conditions, with values within the conditions. So this is a huge F value compared with what we need to exceed over here. And we can again tell what Brian said based on this p-value that it's less than 0.05. So it's significant, but how do we really don't know where the significance is. It's not like a t-test where you just have 2 conditions and then you can say, okay, well, it's significant. Now you have more than 2, so now you have to go the next step with your post hocs. So let's go down here and do that. So I've got this set up for you here. So let's go over what our conditions were again. So condition 3 was our benched row. So why don't we take our values here. The average was 544 watts, and we can just copy our average values in there. Now, when you copy, you have to be careful in Excel because it will copy the formula and everything else with it. So you don't want that, you just want the value. So when you paste, you just go with the second clipboard there, just the value. So we can do that, and in the cells highlighted in yellow is where you'll put those values, those means. Okay, so now condition 1. So why is it that I wouldn't go condition 3 and then condition 2 and condition 1? It would seem logical to put your spreadsheet that way, but when you do post hocs, you go in the order of the greatest value to the least. So the average for condition 3 was the highest. The average for condition 1 was next. And then the average for condition 2 was the lowest. So we're going with the highest average down to the lowest average. So what was condition 2, by the way? What happened on that one? Or condition 1, what was condition 1? Wasn't that the row? Yeah, antagonist row. So basically just doing a poll before you do your press. So we got the value there, got the value there, and then condition 2 happened to have the lowest power output, and so you can copy those values in like so. So the condition 2, remember, was the agonist stretch, and how many of you, I won't go into it, but how many of you studied in other classes why an agonist stretch just prior to a power movement could be a bad thing? You gotta be raising your hands, because we talk about that all the time. Okay, so now we need to go with observed difference. So this is just simple subtraction. So again, equals, and you're just taking this value, 544.2 minus 477.8, and this is your observed difference over here, 66.4 watts. And then C3 minus C2 is right here, minus 436.4. So you're just basically taking the difference between the highlighted cells in yellow. And then C1 minus C2 here. So you have your observed differences. Okay. Okay. So then we are going to run our post hocs. So an equation in your text, page 170, you can do the whole equation at once, but that can be a little bit cumbersome. So I suggest the first half of the equation and then the second half, and then you just put them together to get your critical value. So your critical value is what these differences over here, have to exceed for a comparison to be significant. So you can see the largest difference was between condition 3 and condition 2. So condition 3 was the bench throw, condition 2 was the agonist stretch prior to a bench press. So that was the largest observed difference. And so let's go ahead and just first half of the equation equals, what do I need to type in to take a square root of something? Yep, SQRT. Open your parentheses. What's K minus 1 in this case? Yep, K is your condition, so it's going to be 2. Now don't make the mistake. For the last couple of years, on the final exam in this class, I've given an ANOVA where there's 5 conditions. So don't make the mistake just because in our practice we've done 3. So if you have on the final or on exam 3 an ANOVA where you have 5 conditions, what would K minus 1 be? It would be 4. So just in this particular case, because there's 3 conditions, you have 2, because K minus 1 is 2. multiplied by the F value. You can go to your ANOVA table to get that, or if you have a good memory, you can just type it in, but I'll just click on it. And then close your parentheses. And so you get that, and that's the first half. And then you can do the second half, so another square root, so SQRT. And 2 is the number multiplied by the mean squares within divided by n. N is the number of participants in each condition, so it's 5 is in this case. So mean squares within, you can go up to your ANOVA table to get that. So it's going to be this number right here. So we have mean squares between, and we have mean squares within. So if you're wondering where this F value came from, all you're doing is taking mean squares between, this number right here, and dividing it by mean squares within. So you're just taking this number divided by this number, and you'll get this number right here, is where that came from. So we want lots of variability between, lots of difference between, but not a lot of difference within conditions. And then divide by 5, because that's our n, that's how many participants we have. And then you can that out, and then all it is simply just taking the value for the first half multiplied by the value for the second half. And you come up with 76.59 is your critical value. So tell me where we have our significance. So an observed difference has to be greater than the critical value to be significant. Yeah, so that's the spot. That's where we're pinpointing. Hi, Jordan, welcome. So condition 3 versus condition 2, because that observed difference was 107.8, and so that value is greater than our critical value. So that's where we have significance. So between condition 3 and condition 1, it was close, but not quite, because the difference was 66.4. So it was getting there, but wasn't quite enough. And then the other condition 1 versus condition 2 is 41.4. So again, not exceeding the critical value. So our significant difference would be, so you could then just type in to finish off here, significance between C3 versus C2. And so that would be it for that one. So questions on ANOVA? Yes?
Can I see the first half of the equation?
Mm-hmm. So then you can look up in the formula bar here to 2 times G22. So my only word of caution is you will see more than 3 conditions, either on exam 3 or the final. So just be prepared. Okay, so make sure that you save that. And then let's go into chapter 11.
Even though there's more conditions, it'll still be the single factor.
It'll still be the single factor. So it would be like if we did bench press, but then
5 conditions.
yeah. So, and we'll get later today the other spreadsheet. The purpose of it is intra-class correlation, but it also is an example of what a 2-factor ANOVA would be. Okay, so measuring research variables. So you're all at that point where you're measuring for your own study. And so this concept of validity is really important. So think about what that concept means to you. And that's why we have all of this control in our procedures, is because we want valid results. We want a high degree of accuracy. We want our measurements to represent reality. So the degree to which a test or instrument measures what it is supposed to measure. So we have lots of different ways of measuring characteristics. You think of all the different tools we have to measure different anthropometric characteristics and physiological variables. Some are more accurate, some are more convenient, some are really expensive. So we try to do the best we can. Standardized procedures make it possible for things to be more valid. So a few different types of validity, we'll talk about each one: logical, content, criterion, and construct. So if, as an example, if a study seeks to compare training methods for producing strength gains, the researcher must have scores that produce a valid and unbiased measure of strength to evaluate the effects of the training methods for each group. So the method that you use to assess strength or represent strength is really important. So how many ways can we measure strength? We have to be able to define it as the expression of muscular force. And we can do that in lots of different ways. We can do traditional dynamic assessments. We can also do isometric assessments where there's no movement happening. We can look at strength in terms of how fast force is being produced. We can look at isokinetic measures of strength that are done at a pre-selected velocity. So whatever measure we choose, we want to make sure that people in each condition have an equal opportunity to do well. So if you have one group that trains isometrically for a period of time and another group that trains dynamically for a period of time, that's difficult because you have to be able to choose a measure of strength that is not biased, and so both groups have an equal opportunity to do well. Internal versus external validity has to do with the application. So there's an inverse relationship between both types. Internal validity is, there's a very tight control. Was the study done the right way? In a lab-based setting, internal validity is very high, but sometimes the conditions in a lab don't approximate what happens in the real world. So a lab, you can control temperature, you can control the audience effect, you can control humidity, everything nice and quiet. Sometimes that doesn't approximate what's actually happening outside the lab. So how well do your results apply to a real world type of setting? So there's a real balance between the two. Oftentimes we do what's called quasi-experimental research, which has a good amount of control, not perfect control of everything, but it can be well applied in a practical scenario. So just so you know, there's kind of it's hard to have 100% of both. Logical validity is sometimes called face validity. So face validity is based on appearance. So a lot of you might be testing people that aren't familiar with HHP and what we do. You want your test to have a good amount of face validity. So a normal individual outside of HHP would think that a test of things like a static balance test like this, that we've done similar in lab this week, that consists of balancing on one foot. A normal person would think, oh, okay, I can see that. That's a test of balance. Or a speed of movement test, where you run a certain distance while being timed. So a regular outside of HHP person would know that they're being tested on speed. Okay, content validity is next. This has to do with test batteries. So you have several different tests that are put together and thought to predict an ability. Like the example here is the NFL Combine. The other thing is each component of the test battery doesn't necessarily have equal importance. So, for example, with the NFL Combine, I'm not sure it's ever been determined what test or which test as part of that battery is most important in predicting playing ability in the NFL. So other test batteries may have different amounts of emphasis on a part of the test more than others. So oftentimes field-based measurements are used in studies and frequently validated against a criterion. So we have lots of field-based methods as part of our lab. So even though we have a lab downstairs, we have skin fold assessments that take place in there. That's a field assessment. We have a nice bioimpedance device, the in-body. That's actually a field-based method. But these field-based methods are validated against a criterion, which is what makes them accurate. So skin folds are validated against something like underwater weighing. The in-body is validated against a DEXA scan or an MRI. So the MRI and the DEXA are generally considered the criterion methods. So they're the most valid, the most accurate. And we want a very high level of correlation between the field-based measurement, which is easy and fast and convenient, less cumbersome, and the criterion method, which is generally more expensive, and not everybody has access to an MRI scan, obviously. So we need a way that we can get a good estimate of body fat percentage when we don't have access to the criterion. So that brings us to this concept of criterion validity. Criterion validity has two different parts. The first part is concurrent. Concurrent. So when I think of the word concurrent, I think at the same time. So two different measures that agree with each other. So correlating a field-based measurement with a criterion that is administered at the same time, they should have a high degree of correlation. So what you get with the field-based measurement should be relatively close to what you would get with a criterion measurement. So scores for many field-based physical performance tests are validated against a criterion. Percentage of body composition is a good example. Can you think of any other examples? Let me throw one out there, maybe VO2 testing. So I don't know any high school track coaches that have a $40,000 K5 unit, and that's very accurate as an estimate of VO2 max. But what other assessments do we have, maybe based on time or distance, that we can estimate VO2? Yes, that's one that's based on heart rate, actually. Good. Mile-and-a-half run or 12-minute run. A couple examples that the further you run in 12 minutes or the faster you run a mile-and-a-half, you can estimate your VO2 max. And that should be pretty close to what you'd get with indirect calorimetry in a lab. So this is what a DEXA scan looks like. And so it's very expensive and it takes a lot of time to do well. You have to have a trained technician and very tight control, but you get output that's highly valid, highly accurate for estimating different components of the body, so bone tissue, muscle tissue, fat tissue, and so on. So studies have been conducted to correlate DEXA with the in-body bioimpedance device. And so we have one of these in our lab, and all of you have had that opportunity. And it does, it correlates at about 0.9 with a DEXA scan, so it's pretty close. It's non-invasive, it takes about 3 minutes, and you have a pretty good estimate. So it's really nice. Okay, so a few other things with criterion validity. We want it to be relevant, so we want it to closely resemble the truth or reality, and freedom from bias. So everyone has the same opportunity to do well with a test. It's not biased in some way based on some confounding factor. Okay, so with criterion validity, there's two parts. Concurrent is the first, and the second part is predictive. So sometimes we use the criterion to predict some future behavior. So we give people a test as a way of predicting playing ability or performance at some future point. So that's why we call it predictive. So this figure here, predictive validity. Does the test predict something useful like on-the-job performance would be an example. Entrance examinations. So don't like to think about those, right? How many of you have taken entrance examinations? Yeah. So when I was applying to a doctorate program, I applied to 6 different schools. I only got in one. That was Arizona State, but all it takes is one. And my GRE was pretty terrible in 2 of the areas, but math was like off the charts high. So in my field, that happens to be really important, so that I was able to get in. But entrance examinations aren't very fun. I heard you talking about a certification exam. It's kind of the same thing. It's several hours and it's terrible. But you get through it. It's just hoops that you have to jump through in life like everything else. So prediction equations are often used to predict a criterion variable from a predictor variable. So in this case, the criterion would be performance in college, whereas the predictor variable would be your entrance exam score. So we spent a lot of time in this class on prediction equations, and once you have your prediction equation, the best thing you can do is undergo this cross-validation procedure. So you make a prediction equation with a good sample, and then the next thing you should do is take another sample of people that are similar and use the prediction equation on them to see how accurate it is. So you have a sample of lifters and you form your prediction equation, and then you take another sample of similar lifters and you apply that prediction equation to see how well your prediction equation works. So that's called cross-validation. Okay, so very last type of validity is construct. Construct validity. So a construct refers to a concept that is associated with a range of behaviors. So the example that I included is sportsmanship. Okay, so it's a construct is established by relating test results to a range of behaviors. So a range of behaviors in this case that would be associated with someone with a high degree of sportsmanship. So sportsmanship is the construct. And so you would look at behaviors, all the behaviors that would be associated with that particular construct. So another example here would be the construct of anaerobic power. Anaerobic power. So you could establish that construct by asking different groups of athletes. Okay, so distance runners, sprinters, jumpers, large numbers of people is required to take this test to determine differences, and so that would help establish this construct of anaerobic power, because characteristics of certain groups like sprinters, you would expect those athletes to have certain qualities that would be correlated with a high level of anaerobic power. Okay, so after reliability, the next important thing is reliability. So we have validity and reliability. Reliability is consistency. Consistency. So if a person takes a test 2 days in a row, are they going to get the same result? They should. So if they went down and did the in-body today and then came back the same time tomorrow, you would hope that their score would be very close, very close. So that's why we do all these things like make sure that you go to the restroom before, because the amount of water in your body can affect that. So we want the conditions to be as similar as possible over repeated days. So a test cannot be valid if it's not reliable. However, a test can be reliable without being valid. So can a test be consistently inaccurate? Yeah. So that's why we go through all those calibration procedures and standardized protocols is so that we get both a valid and reliable assessment. So the target analogy I like to use, this would be reliable but not valid. So you see that the center of the bullseye represents truth or reality. So that's what you want to hit with your test. So the dot represents the test result. So you want to hit the bullseye with your test result, and you want to hit the bullseye consistently. So then you're reliable and valid. This is both reliable and valid, where you have a consistency as well as accuracy in your measurements. So sources of measurement error can lie with participants. So I want you to think as you get ready for your data collection, I want you to think about conditions. I want you to think about the time of day that you're collecting data. Maybe the state of mind of participants, the location where you're collecting data. All the little things that could make a difference in creating measurement error. So the testing conditions need to be as consistent as possible in every way. Measurement error can lie with the testing method. So what if you have someone running a stopwatch and someone assessing something else, and then the next time they come in to test, you switch roles. So someone else is running a stopwatch and you're testing something else. You need to make sure that the people judging the test result are consistent each time. So intra-rater reliability. The scoring method. Okay, so make sure that everything is laid out to begin with about what you're doing, why you're doing it. Give them an opportunity to ask questions so that they're aware, and don't change your methods between one day and the next day. instrumentation, so just making sure that everything works. Calibration, if you need to. Okay, so these are subjective things that we can do to increase reliability. There's also objective ways that we can increase reliability. So we call this the intra-class correlation. So this is not like the Pearson R. The Pearson R is called the inter because you're looking at between two different variables. The intra is looking at the same measurement over repeated days. So that's a different type of correlation. It's not the same where you're looking at different tests. So the Pearson is used for different tests. The intra-class is used when you're looking at the same test done repeatedly. So let's say, just an experience, it's really difficult if you're using novice people in a strength training study. Anybody know why? Especially when you are testing for the first time. So day one, they get a certain result. They come back 3 days later, and guess what? They're a lot significantly stronger. And then they come back 3 days after that, and guess what? What's going on with those novice bodies? Why are they getting stronger almost on a daily basis? What's happening? Physiologists. Yeah. Upregulation of motor unit recruitment and all those things. Muscle fibers that they've never used before, all of a sudden available. So the brain is allowing access to all these new muscle fibers, and so all of a sudden, almost on a day-to-day basis, their measurement is improving. So if you're using novice people, what would you do? Because eventually, are they going to just keep like that? Or no, you have to give them that initial time period to kind of get to a point where they can be tested and it's going to be consistent. So advanced people, it's usually just 2 sessions. So an advanced lifter comes in, they test, and then maybe come back 7 days later, they test again. It's usually going to be about the same. Novice lifter, you really have to have that time period for them to get used to it, to where they have some consistency. So with that being said, let's, part 3 of class today, we need to calculate this intra-class correlation. So I want you to go right here. So this other spreadsheet, the intra-class correlation practice spreadsheet. So, so if you read the directions here, intra-class correlation procedure, perform a 2-factor ANOVA without replication using the data analysis function. So we're using a 2-factor ANOVA in this case to get our intra-class correlation coefficient. So the 2 factors in this case would be the day 1, day 2, day 3. What would be the other factor? So 2-factor ANOVA. We have 2 factors. We have day and load are the 2 factors. So that's different than what we did with the single-factor ANOVA earlier, where it was just 1 load with different conditions. In this, we have 3 days, and we have 5 different loads. So 2 factors, days and loads are the 2 factors. Under days, we have how many conditions? 3. Under loads, we have how many conditions? 5. 2-factor ANOVA. Other people would call this a 3 by 5 ANOVA. I like just saying 2-factor. We've got 2 factors, but we may have multiple levels or conditions under each factor. So what we're doing here is we're trying to determine consistency between days. So we're going to run a two-factor ANOVA to find out how consistent we are from day 1, day 2, and day 3 across loads. So what you would expect is that, or what we're hoping for, I wouldn't say expect, but hoping for, is that there's no difference between columns, but you're probably going to see a difference between loads. So we can do a two-factor ANOVA and we can look at power between loads, but we can also look at consistency across days. So columns would be the days comparison, rows would be the loads comparison. So two factors. So really what we're after is we don't care too much about loads. What we want is consistency across columns. So that will tell us that day 1, day 2, day 3 values are not statistically different. So this is a case where we don't want difference, correct? Because we want day 1 to be the same as day 2, to be the same as day 3, not significantly different. So let's go ahead and do that. So you can see down here eventually the intra-class correlation. So if you look at formula 11.1 from your textbook on page 210, this is where that formula comes from. But let's just run our analysis here. So data analysis. And so you want to make sure that you click on the correct one. So it's a two-factor without replication. So you might be saying, what is that? What does without replication mean? That means that for each day we only have one score. So with replication would mean that for each day we might have 2 scores or more than 1 score. So just remember without replication, 1 score on each day for each load. Okay, so let's go here. So two-factor without replication. And we're okay, so we can say okay. Input, so we want the whole thing. So we want everything you see here. So column headings, all the rows. Let's put our labels in there. And let's select our output. We could probably just go right there. Enter. And we get all this two-factor without replication. Is everybody okay so far? Everybody get the output with the two-factor like what we have up here? Make a line up here. How you doing, Ashley? All right. And you guys?
Oh, if I'm trying to not do something.
You gotta get that up again, maybe? We could,
Because usually it'd be like right here. Like that.
let's see, yeah, you could click on that, check for updates, get rid of it. And then you could, maybe you just need to load it in there again, so you could go to home and there should be an options tab or something. How are you, Brian? Got it good? Okay, I'll show you what to do. Okay, did we do okay?
Yeah.
So let me explain. It's important, most important thing is to understand what's going on here. So let's go down to this ANOVA table right here. Okay, so we have rows. Remember, rows represent different loads. We have columns. What do the columns represent? Days. So I want you to change this to be a little bit more clear. So you could put, rather than rows, you could put loads. Rather than columns, you could put days. And so that will help with a little more clarity with that. So let's go over here. So do we have a significant difference between loads? We hypothesized that there probably would be. So between loads, we go over here and our F ratio is huge versus our critical value. And secondly, we could see the p-value is less than 0.05. So yeah, there is a significant difference between loads. We're not really interested in that though in this case. We're interested in consistency between days. So if you're taking a group of people and testing them the same way 3 times, if you want to be reliable, it should be consistent. If it's consistent, should it be significantly different? No, it should not. If it's consistent, you shouldn't have a significant difference between days. So, do we have a significant difference between days? No, we do not. So if you follow the days, the day 1, day 2, day 3, you go across here. The F is 2.68, the F critical is 4.45, the p-value is 0.12, so it's not significantly different. Is that a good thing or a bad thing? That's a good thing if we want reliability. Not significantly different between days is a good thing. So how do we take that and come up with our intra-class correlation? You just got this handy-dandy formula from your book here. So the mean square for columns minus the mean square for error divided by the mean square for columns. So we can take that and just start. We'll get our equals and open parentheses. Now remember, which word did we replace for columns? Days, yeah. So we want mean squares for days, because that's what the columns was, minus the error. So you can see the mean square error right here. So this 26.86 and so on. I like that one. And then close your parentheses and divide by the mean squares for columns. So you just click on that one again. And come up with 0.6277. Is that terribly good for a correlation? Not real good, but good enough. What do we say is a strong correlation? 0.7 is what we want. And if we're talking reliability at the beginning of a study, 0.9 would be nice, because that says the day 1, day 2, day 3 are almost the same. They're not significantly different, which is good, so that's a start, but the correlation isn't super high either, probably because of the small sample size with this particular study. So, does everybody understand or have any questions? Do you understand how to calculate this? Do you understand why we only care about days in this case and not loads? Okay. All right. Any other questions? Okay, so make sure that you save this, because that's your cheat sheet for the exam. Okay, all right, have a good weekend. That's all I got for you for today. What's due on Tuesday? Chapter 11 questions, all right. So you can find those just again right here in the March 31st folder, D2L.